Hi, welcome to the Signal Path. In this episode I'm going to do another product review for you guys. I'll be reviewing the brand new Keithley 2450 source meter with touchscreen. This is the successor of the popular Keithley 2400 source meter, and they've made some drastic improvements on this unit. They've modernized the interface, and now of course it has a big bright color touchscreen as well, enabling quite a bit of interesting interactions between the user and the instrument. And as it is with every review that I do, I make sure that I've had the instrument for quite some time and I've been using it in my lab and I've been experimenting with it. You may have seen it in the background of some of my other videos, but I want to make sure that I really test it to its limits and play around with it to make sure that my review really covers all the critical aspects of the unit. And also I'm going to do, as always, much more than just showing what the menus and what the specification of the unit is. We're going to do industry and research relevant experiments to showcase the instrument's unique capabilities and some of its features. And this has several advantages. Not only will you see the instrument in a real world environment, but you also may learn something from the experiments themselves. And I explain a couple of different things about each of them, and there may be some slides explaining exactly what's going on in each experiment. So I think it's going to be really interesting. Now we're going to start slow, doing some basic things, but towards the end of the video we're going to do some really complex and really interesting experiments. So don't run away and try to watch it to the end, because all the cool stuff is towards the second half of the video. So let's get started. So what is so special about a source meter? Sometimes when I discuss the uses of a source meter with people, they ask me, well, why can't I just grab a power supply and put a multimeter in series with it or in parallel with it and then have basically a 6.5 digit measurement of the current and a 6.5 digit measurement of the voltage? Well, not only that is, 3 instruments, aside from that, a power supply is a one quadrant instrument. Most power supplies are, essentially meaning that they will give you positive voltages, which is shown on this axis, and positive currents. So current can flow out of the instrument when it is providing positive voltage. Sometimes people say the power supply are 2 quadrant instruments because they can also do negative voltage. That's true. If you reverse their terminals and they have isolated terminals, you can get negative voltage from them. But you cannot do that in a single sweep. So you cannot sweep from the positive voltage to the negative voltage in a continuous sweep. You'd have to disconnect and reconnect the terminals. So in reality, most power supplies are stuck operating in this region. But a source meter, a true source meter, is a 4 quadrant instrument, meaning that it can supply positive voltage and positive current, or negative voltage and positive current, or negative voltage and negative current, or even positive voltage and negative current. So you can imagine positive voltage and negative current is an interesting thing, because that's kind of be like applying a voltage to a battery, something that will give you current back as you try to set its voltage. So being able to travel in all of these 4 quadrants allows you to get a true IV characteristic of any instrument that you want. So for example, I can sweep, something from here all the way down to here, or I can sweep something that, travels in all of the 4 quadrants depending on what instrument you're measuring. So it is a truly versatile instrument from that regard. And what is also special about the 2450 is that it has a really wide operating range. Its power envelope is quite expansive. So it can give you plus and minus 200 volts, and in that range it can give you up to plus and minus 100 milliamps. Or if you limit yourself to plus and minus 20 volts, it can give you all the way to plus and minus 1 amp. So it has about 20 watts of output power, and it can give it to you in any of these quadrants, of course sweeping in any direction. And that is what is special about a source meter, and it does that at remarkable accuracy and resolution. It has easily 6.5 digits of resolution. So let's go ahead and take a look at some of this specification. I'm not going to go into detail, just point out some of the important things. When you're sourcing voltage in the 20 millivolt range, it has a resolution of 500 nanovolt and a noise of only 1 microvolt RMS, which is tiny. And you can do really sensitive measurements. Even when you're setting it in the 200 volt range, you can increment it by 5 millivolts at a time, which is also extremely impressive. But what is really interesting, I think, is this ability when it comes to measuring current and also supplying current. So when it's measuring current and you're in the 10 nanoamp range, your resolution is 500 femtoamp, but it can measure 10 femtoamp steps, which again is a very small resolution. It can give you really accurate measurements. So you can go ahead and look at the specification. It covers a really wide range, suitable for many different applications. And if you compare to the 2400, which it is replacing, they have improved almost every aspect of the instrument. For example, the minimum current has gone from 10 picoamp to 10 femtoamp. which is a big difference. The maximum current remains the same, but the voltage measurement capability has gone from 1 microvolt to 10 nanovolt, which again is a big difference. They've also done quite significant improvement in the accuracy, and you can go ahead and double check that and see what you can do. But the other thing that is really interesting, which I'm going to demonstrate extensively in the review, is that you can connect multiple units in a TSP link. And what that allows you to do is it allows you to connect only the first unit, and here is shown with the GPIB, but it can be USB or Ethernet. You can connect the very first unit to the computer and then daisy chain multiple units using a TSP link. On top of that, these instruments can run scripts, meaning that you can download the script to the instrument and then say run, and the instrument will then do all the running and store all the variables and process all kind of complex algorithms that you've written in your code without having to communicate back and forth to the computer. This is a huge advantage in a production environment and can speed up your measurements and your experiments by up to 4 times, because it doesn't have to send commands back and forth to the computer. All the triggering between the units, as well as between the unit and the computer, they're all handled automatically in the background, and when everything is done, you can go ahead and grab the data, which is a really big advantage. So let's go ahead and take a closer look at the units. So let's familiarize ourselves a little bit with the Keithley 2450 source meter. Here I've placed 2 units on top of each other, so you can see the back and the front of the unit simultaneously. I also have placed a 2400 source meter right next to it, so we can do a direct comparison between these 2 instruments. The Keithley 2400 has been an industry standard for a long time. You can find them in research lab and production labs all over the world doing complex characterization work, but its interface was getting rather dated. If you've never used a source meter before, if you had never used a 2400, it took some time getting used to figuring out how to navigate through the menus and get the different settings. It really was time to upgrade the interface and really modernizing it, making it easier to use. And Keithley has done an amazing job going from the 2400 to 2450. They have completely rethought the way the user interacts with the source meter. The GUI they've designed makes it extremely easy to manipulate the menus, get the different settings, do quick settings, or set up really complex measurements. I've been using this for quite some time now, getting myself familiar with it and preparing for all the experiments we're going to see today, and I am extremely happy with it. And so what they've done is that they've replaced the VFD display with a 5-inch color LCD screen, and on top of that, this is a multi-touch touchscreen, so you can do things like swiping and pinching, to pinch to zoom in and out of different graphs that are shown on the display. It's really easy to navigate different menus, and you can swipe a different menu left and right, get access to quick settings and so on. They've also gotten rid of all these buttons that used to be here, the voltage, the currents, setting the triggers and the sweep. They got rid of all of that. Everything is now handled through the custom UI that they've designed, making it really easy to get to the setting you're looking for, as opposed to kind of guesswork that used to be the old 2400. And on top of all of that, they've also improved the analog performance of this unit significantly, and I'll show you some of the improvements of the new 2450. What they've kept is that they've kept 8 buttons, which allows you to jump to different GUI settings. These buttons, the home menu, quick set help, enter, exit, function, and trigger, I use these buttons all the time. These were good choices. Sometimes manufacturers put a button on the front that you never ever use, but I find myself using these all the time. So good choices for that. I'm pretty happy with it. What also they've added to the front panel is that now you get a direct ground connection, which the old unit did not have. Both the switching between front panel and back panel connections for doing a measurement is still handled through a soft switch. There's an internal relay that switches back and forth just like the old one. And of course the output on and off button is there with a big blue light that lights up. Again, like the old model, they kept the color from that one, I guess for familiarity. And what they've also added is this multifunctional rotation knob, which also is a push button at the same time. And this thing feels great. I know it may not seem very important, but the fact that this has such nice distinct steps is extremely important, because the last thing you want to do is to rotate something and have something jump 2 units instead of 1, and either damage your circuit or get a measurement mistakenly in the wrong voltage setting or current setting. So this is very nice. It feels great, and it looks to me that it's going to be something that's going to work for many years to come. At the back of the unit, they offer every kind of interface you would ever want. So you have Ethernet, you have USB. The digital I/O unit is for setting up external triggers and so on. There's a bunch of digital I/Os which you can connect to a whole bunch of other units and get complex triggering action, and I'll show you that. There's also the TSP link, allowing you to daisy chain a whole bunch of 2450s and talk to all of them and program them all through a single interface to the computer. A huge advantage of this, and I'll talk about the scripting of these instruments later, which is a unique Keithley feature, extremely useful, extremely beneficial. If you've never used it before, as I'll show you in the experiments, you're gonna love it. I certainly do. And there's also a GPIB unit at the back. They've included this for backward compatibility, of course. If you already have a 2400 source meter and you've written a whole bunch of GPIB code for it, don't worry, the 2450 supports the Skippy language code that the 2400 used to have. So you can set it to behave like a 2400 in terms of the Skippy language. So you can use your old code, you don't have to throw it all away. So the transition from the 2400 to 2450 should be rather easy. Here you can also see, of course, the 4 connectors which represent these 4 connectors here. These connectors at the back are triacs. So they have 3 layers of conductors, and you can see there's a diagram underneath here which tells you exactly which each conductor is connected to. On the sense high and the force high, the middle conductor is connected to guard, allowing you to do very sensitive measurements by providing a guard voltage around your enclosure, around your device that's under test. And you've seen me use the guard function on a different experiment, on a different video. Now, without it, you cannot do extremely sensitive measurements and extremely low currents, which prevents, you know, things like leakage and noise to come into your circuit. And you can see that the outer one is connected to the earth, ground, and so on. So everything is pretty well explained. The only other thing at the back here is that interlock. The interlock function is a switch essentially internally that either enables or disables the instrument to provide you more than plus or minus 50 volts. They've done that for safety reasons. So if the interlock is disabled, the unit will max out at plus or minus 50 volts. It will not go above that, which is safe to touch essentially. And also it lowers the chances of it damaging whatever it is connected to. If you enable the interlock, then the unit can go to plus or minus 200, making it much more dangerous. So it's useful in a training environment, a university environment, to have an interlock that's disabled, so that it's by default disabled. If it's unplugged, it counts as being disabled, so that you don't accidentally damage something. And Keithley will send you a little connector like this, which you can use, which directly plugs in there, and you can put cables in here and have them connected to something else to either dynamically change the interlock or have it or permanently switch it. So in my unit, what I've done is that I have essentially taken the interlock and I've connected it with a cable like this, like so, just to a little switch here, and I've colored it so if you put it in the red it goes to 200 and the green it doesn't. So it's just a little protection. It's nice. We're going to use both of these all the way up to 200 for our experiments, so I'm going to have the interlock enabled on both. The unit also gets shipped with a little cable like this. It's a Cat 3000 volt cable with a hook selector in the front, which is a really nice quality cable that comes with it for bench use, typical bench use. You can plug it into here and do your testing and so on. One last thing I wanted to point out is that there's actually a couple of LEDs behind this panel right here, and while I was talking about the interlock, so there's an interlock LED that will light up if it's enabled, warning you that the unit can go to 200 volts. There's also a remote LAN and a 1588 connector sitting here, which tells different kind of activities in the front. You cannot see the lights, but they're behind the front panel and they light up. Well, I'm sure you're all waiting to see the experiments. I just wanted to go over this. Well, let's not wait any longer. Let's go and see what we can do. So I've placed both of these units in the lab. The top one is connected to the computer via USB, and the bottom one is connected to the top one through the TSP interface. As it is with the TSP interface, only the master, the very first unit in the daisy chain, needs to be connected to the computer. The instructions for all the other units are sent from the master unit. So let's go ahead and take a look at the first one. I'm going to turn it on. I just want to briefly show you some of the menus and some of the options of the instrument, mainly because they've spent so much time creating a coherent and easy to use interface. And I think it's worthwhile just familiarizing ourselves for a few minutes and seeing what are some of the basic things that this thing can do. So you can see it boots up in a couple of seconds, so it's ready to go right off the bat. And this is the home screen that you're dealt with. So if you press home, that's basically this screen that you're looking at. At the top it's showing the measured current, and the bottom the measured voltage, and you can see things like auto ranging and so on, and source is right now set to 0 volts and the limit is at 105 micron. You can also see a couple of dots in the middle. These are the menus that you can swipe left and right on from the home screen. So if I swipe left, for example, I will get the settings menu where I can do things like filtering, mathematics, and the number of power line cycles that it does integration over, relative measurements, and so on. For example, I can change the display digits from 5.5 to 6.5 digit. Now I get an extra digit here at the top. Added to the list. If I swipe again to the left one more time, then I get the statistics menu, and in the statistics menu I see things like average 7.4 picoamp right now because there's nothing connected, and you can clear the statistics, some basic readings here that you would expect from a statistics menu. So let's swipe left again, left one more time. Now this is the main source voltage, and I can see it has an added digit because I changed it to 6.5, and I go left one more time, and now I get the trends menu. In the trends menu, by default, it's showing the trends of the measurement versus time. This graphing menu will change depending on what the instrument is doing. So if you're doing things like a particular IV characteristic, it will change the X and Y axis accordingly. And if I swipe one more time to the left, I get the users menu, and in the users menu you can program your own text in here using this script from outside the instrument and report additional measurements or some kind of a message to the user that's doing the testing if it's not connected to the computer at all. So let's go back again to this trends menu, and if I swipe up, then the trends menu gets maximized, so you can see now a full screen graph, and you can do things like spanning the graph from looking at older measurements, or zooming out so you can see more measurements in together, or zooming vertically this way. All the typical things you would expect to do on a multi-touch screen instrument that is showing you some kind of a graph. So extremely useful, really easy to use, and logical. And if you go under data, you can change what the x-axis and y-axis and so on is, and you can even add your own markers into it. And of course on this scale you can change what the overall scale of the instrument is. And you want to go back to the same menu again, you click home and brings you back here, and you can swipe again to the left and you see the source voltage. The touchscreen works quite well. It rarely makes mistakes. I'm quite happy with it. Some additional information is also shown. There is a little message center here. If you click, it tells you what all the messages that have come through the instrument. So you can see there's two informations. The reading buffer is 0% filled. It just means the buffer is empty. But if there are errors or warnings and so on, they all show up here, and you can change the settings of it, and the basic stuff. Very useful, easy to handle. And then there's also tells you that there's no script running, that the buffer is being written to the default buffer 1, and there's an entire trigger menu where you can set advanced triggering. Right now it's set to continuous trigger. We'll talk about that later. So once you're familiar with the main screen, then you can go to the main menu. And the main menu, what they've done is that they've broken the main functionalities of the unit in a bunch of icons in a GUI interface that is very logical. So it's broken up into system, scripts, trigger, views, measure, and source. So let's say you want to change the way the instrument does measurement. How does it collect data from its measurements unit inside? So you go under measure settings, and then now you can change things like the measurement range, the limits, whether it's auto zeroing, a number of power line cycles, whether it's 2-wire or 4-wire, really easily. You want to change how it does the sourcing. You go under source and you can see a whole bunch of additional settings for that. So they've really broken it up and made it into the small compartments so you can get to what you want really quickly. Another really nice feature is that it has these functions called quick set. And under quick set, what you can do is you can turn the instrument very quickly into either a voltmeter, an ammeter, an ohmmeter, or a power supply, because this thing is capable of doing any of those, of course, and it's just that once you have to configure it accordingly to get it to do any of these, and this will quickly set those functions for you. And you can get, since it boots really fast, you want to use it as a multimeter briefly, no problem. You want to measure its power supply, you can use it as a power supply. Very, very easy. Or you can set its basic function. So if I click on this function button here, it's asking me, do you want to source voltage and measure any of these, or do you want to measure current? You want to source current and measure any of these? You can really quickly and rapidly set it to those. And also you can here see that you can change the performance with respect to how fast you want to do measurements. So if I don't care about resolution, I can tell it to do measurements at 3.5 digits but get 1700 measurements per second. Or if I want a 6.5 digit, I can get 6.5 digit at 1 reading per second. Or a little bit slower, a little bit faster, slightly lower resolution internally at 6.5 digits, still reporting it to you. So really easy to use. And then of course inside the menu there's a whole bunch of other things, and we're going to take a look at them, quite a few of them. And you can see you can set sweeps really easily, and we will get some experiments going on. So let's start really basic, and then we'll work way up and get some fancy measurements at the end. So let's measure some resistance. Let's measure a very, very small resistor. So this is a 0.01 ohm resistor. This is a particular resistor intended for sensing current, as you may be familiar with it. It actually has 4 terminals intended for current to flow through 2 of them, and the other 2 being used for sensing the voltage across it and then calculating how much current is going through it. This is a 1% 0.01 ohm resistor. So let's go ahead and set the instrument to the appropriate setting. I can go ahead and connect it first. So this is the main source. So I'm going to connect the source to 2 of its terminals like so. And it's as close to the resistor as possible. And the other sense I'm going to connect across the sense terminals of the resistor itself. There it is. So it's all connected. You can lay it down like this, sitting right here, making sure you know that these are not touching each other and so on. Perfect. So now we can go under quick set. And then we can say we're looking for an ohmmeter, like so. Then it's going to ask us, do you want 2-wire or 4-wire sensing? Well, since we're setting in a 4-wire and measuring such a small resistor, we're going to go 4-wire. There it is. And then, voila, gives us 0.0103, which is within specification. But if you don't want to do it this way, you want to put more current to it to get even more resolution, that's easy to do. I can go ahead and as soon as I click here, and I try to change the source current into the resistor, it's telling me, do you want to switch to manual mode? I say, sure, let's switch to manual mode. And in the manual mode, I can now tell it what current I want to inject. Let's go maximum, 1 amp, since this resistor is easily rated for that. There we go. We're going to inject 1 amp in it, and then we're going to set the limit of the voltage to be set to 1 volt. There we go. Now I can go ahead on the menu, and I can set the measurement to 4-wire mode. There we go. Go back to home screen and enable the output. There it is. Now it's telling me that it's 0.01002. It's dead on, exactly correct, and the current is 1 amp. Really, really easy, straightforward way to measure resistance. So let's go ahead to the other end of the spectrum and try and measure a 1 gigaohm 1% resistor that I have here. I shouldn't really be touching this with my fingers, but I'm only going to touch the end of the leads. So let's go ahead and put this into this little jig that I made. It's a very, very short distance between the terminals, and really for measuring very large resistors you have to use the guard voltage and put it in a shield and all that for the current not to escape. But anyhow, let's do a quick measurement here for our purposes. I just want to show you something about the instrument. Here we go. Put this guy in here, nice and close. Okay, now we can use the menu. Let's go to quick set. Let's set the performance all the way down to 6.5 digit and tell it that I want to source voltage and measure resistance. Perfect. So now if I swipe to the left, you can see that it's now 6.5 digits. Go to the right. Now it's going to enable the output. Now, whenever you want to measure a large resistor like this, you have to put a large voltage across it, simply because the current that flows through it is so small that it often falls below the sensitivity of the instrument that you're using to measure it. And putting a large voltage across a resistor like this will create a large dissipation, the resistance will shift, not to mention that it can arc and other bad things can happen to it. But check this out. I'm going to put only 1 volt across the 1 gigaohm resistor. Look at that. No problem, and this is indeed correct, and you can see that even with 1 volt it's going to slowly shift around, go up a little bit as the resistor warms up. But you can see it has no problems measuring very, very large amounts of resistance without any trouble at all. So let's go ahead and see what kind of resistance this jig that I have here actually has itself. This is a warning that you cannot do measurements when the output is turned off, which we already know. Let's go ahead and take this guy out and turn the power on. So 38, 30, 50 gigaohm is telling me, you know, it's in the, and it's going to continue to charge because it's charging up, so the current is not actually changing. Now it's telling me it's in the teraohms. It's because charge is now building up on the terminals, so that of course the current flow is going to continue to drop, and that's what you're seeing. You can see the kind of values this thing can report to you are in the teraohms. I mean, it's amazing. It's incredible. If I go ahead and increase if I put 100 volts across it, now there's going to be sufficient leakage current through here. You can see that it's going to slowly build up again until it's charged to 100, and then it's going to stabilize. Whatever it's going to stabilize at is going to be the leakage current through this little jig that I have here. You can see, you know, it's probably going to, I wonder when it's going to stop, maybe just over 100. Let's see. It's going to keep going for a bit until it stabilizes. But you can see that and this is not even distance. I'm not using any of the guard voltages, which you should be if you're measuring resistance of this size. But the sensitivity, the noise floor of this, and its accuracy is simply remarkable. So for the next experiment, let's do a sweep. here I have a mystery diode. You can see right like this. It's just connected to the positive and negative terminal of the instrument. Very straightforward. And I want to create a sweep to characterize the IV behavior, IV characteristic behavior of this diode. Let's see how easily we can do this on this instrument. So let's go ahead and look at the menu. I'm going to move this out of the way so the reflection is not on the screen. And here we go. So let's go ahead and go under menu. And I want to generate a sweep. So I click on sweep. And it's telling me if I want a linear sweep. I do. It's a basic linear sweep. I want it to start at, let's say, minus 5 volts, like so. And I want it to stop at 2 volts, like this. I'm going to sweep up a little bit. Step by step, what step do I want? I want a 50 millivolt step. No problem. And it's an automatic delay. You know, it gives you help underneath on what each of these buttons mean. One time is fine. And I'm going to limit the maximum amount of current to 10 milliamp because I don't want to damage the diode. And I'm going to tell it not to abort when it reaches the limit because I know the diode can handle the 10 milliamp value, so it doesn't need to abort when it hits the limit. Okay, well, it's all good. Everything's set up nice and easy. I'm going to say generate. Now it's going to generate the sweep list and the trigger behavior of the instrument. It's going to store it. Now the instrument is ready to go. If I click on home, it's just now waiting for me to initialize. You can see it says idle. It's waiting for me to initialize the measurement. Okay, no problem. So again, here it is. I'm not changing anything. Let's go ahead and press trigger. There we go. So you can see right off the bat that it's at the limit, and then the limit quickly drops, and you can see the voltage is going from minus 5. Now it's going to reach 0, and when it reaches around 0, it's going to slow down. And the reason it slows down is because it's now measuring really small amounts of current, so it needs more time to integrate the appropriate amount of charge to be able to give you an accurate measurement. And now you can see that it hit the limit, and it's done. And while it was doing, I could have actually swept and looked at this curve before, but now I can look at the curve in more detail. I'm going to sweep up. Look at that. So the first thing I noticed is that this wasn't an ordinary diode. This was actually a Zener diode. Why? Because you can see that it has the reverse breakdown voltage. And it has a specific breakdown voltage depending on the Zener's breakdown voltage, which is what defines its characteristic. On the forward bias part, let's go ahead over here and let's zoom in here. You can see that once the diode hits about 0.6 volts or so, it becomes forward biased and the current exponentially increases. That's normal. That's how a diode is supposed to behave when it's forward biased. But this also has reverse bias breakdown, and you can see right around here or so, around 3.7, 3.6 volt. And in fact, I know that this is a 3.5 volt Zener diode. The current will increase quite rapidly, and once it reaches the minimum value, so it's already, you can see it's maxed out at minus 10 milliamp. Otherwise, it would continue to go down. I've limited it intentionally to that value. And now I can zoom in and take a look at it. I can go back there and auto scale it again and go back to the graph. And there it is. This is really impressive because I don't know if you've used a 2400 before, but this was not possible in such an easy way using the 2400. They have drastically improved the way this instrument interacts with the user. And you can go ahead and make even more complex different types of sweeps and so on. But enough with these basic tests. Let's get fancy. Let's do an IV characteristic of a transistor. So here's our setup for the next experiment. I've turned off some of the lights to avoid reflection off the screens. So what I've done here is that I've taken an NMOS transistor, an n-FET transistor, like so, and I've connected it directly to channels of the two source meters. So what I have is that I have the gate source voltage of the MOS transistor connected to the top source meter and the drain source voltage of the MOS to the bottom source meter. This allows me to run a two-dimensional curve, a two-dimensional IV characteristic where I can change the VGS and see its impact on VDS or vice versa. And what it allows me to do is that I can look at things like leakage current, I can look at the forward bias current of the transistor, I can look at its threshold voltage, I can find out when it enters triode, what the triode resistance is, what its output conductance is. It will be a complete IV characteristic of the transistor across all possible combination of all of these three terminals. And you can only do this with a two-channel source meter, so you would need two of these together at the same time. Now, instead of programming it through the front panel, what I'm going to do is I'm going to use the Kickstart software, which we talked about a little bit before, and Kickstart software automatically recognizes daisy-chained source meters, which these two are, and it will detect them as different channels. So here you can see that it has detected SMU1, channel 1, that's the gate source voltage, and has detected SMU2, channel 2, which is a drain to source voltage. And I have configured the instrument to go from 1.7 to 2.1 volt on the gates to source voltage. The reason I'm starting from 1.7 is because below 1.7 the transistor is essentially off. So you can measure the leakage current under that condition. I wasn't too interested in that at the moment, so I just set it to 1.7 volts. And on the second channel, the drain to source voltage, I go from 0 volts to 5 volts. This will take the device and go through the triode to the active region, because the VDS starts to be 0 volts, that's in triode region when the device is on, and all the way once it passes the overdrive voltage, it will enter the active region. So then in that case, we should be able to see the classic IV characteristic of an NMOS transistor as a function of VGS. So this will be a two-dimensional sweep. So we can go ahead and run that and take a look and see what is going to happen, and I can plot everything and we'll see it. So run this thing. Here we go. Click on run. So now you can see that the instruments kick into action, and it's going to start with, you can see that at first it starts setting the VGS to 1.7 volt, and at the bottom you can see VDS is sweeping. Now it's switched to the next VDS voltage. Once again, this is sweeping. So this is going to continue doing these two-dimensional sweep. And if I go on the graph here, we can see it live in action. Look at that. You should be able to, if you're familiar with transistors and device physics and so on, you should immediately recognize this curve. You can see that here VDS as a function, and this is measuring VDS and this is current, so you can see the current goes up linearly at first when the device is in the triode region, and it flattens out when the device is in the active region. And you would expect the slope of this curve to gradually get higher and higher, meaning that the output resistance of the device is going to drop because there's more current in it, and output resistance of a MOS transistor is a function of its IDS current through this drain and also a function of its early voltage gamma. So you can see that the slope is going to continue to increase, and this curve is just being slowly built up, and the sweeping is going to continue. And even here I can see, for example, if I sweep to the left, you can see directly what happens in between each of the sweeps. So at the bottom point here is when the VDS is 0. You can even see it right here. So the device is in triode region, active region, triode region, active region, and it's going to continue to do that as a function of different gate to source voltages. So we're going to wait a little bit longer. You can see the curves are being assembled, and look, you can clearly see how the slope is continuing to increase as there's more and more current through the device. Now there's up to 400 milliamp through the device. You can see VGS is now at 2 volts. Now we are at half an amp, and it's going to continue to increase as the VGS goes up. Remember that the IV characteristic of a MOS transistor is a quadratic equation of its VGS voltage. So, and we should be able to see that. And if you look at this curve and if you plot the transition between triode to the active region, you will get a quadratic curve. Again, this is all electronic stuff. I'm not going to go too much into detail. You should be able to familiar with that. So look at that. There you go. Now it's run. Look at all these curves. It's a perfect IV characteristic of a transistor. No problem at all. And you can see how fast it was. It literally took me a couple of minutes just to set this up and look at it. Now we can do other kind of things. We can plot basically everything versus everything, although this is the most meaningful value. But on top of this, for example, I can superimpose the voltage of the gate. There it is. So you can see these are all the gate voltages, and I can actually superimpose the gate voltages on the other axis too. I mean, it doesn't really matter. So for example, here's the gate voltages that, it shows up now on this axis. So these are all the voltages you jumped between, and these are all the currents that you see. So you can plot anything versus anything. And once you're done with it, you can go ahead under sheet menu, and you can actually copy all of the data directly into Excel. You can save it as an Excel format file up here, or as a comma separated format to analyze in a different program. You can add your notes and so on. So I like the software. The only complaint I have is because it's a little bit buggy sometimes. I think this is in its infancy. So once it develops a little bit more, hopefully the bugs will go away. Sometimes it can't communicate with the instrument, or it does something weird and doesn't update the graphs properly. But I think it's going to get fixed. For now, it's great. So let's do something different. So for the next experiment, we're going to look at some hysteresis effect. Now, hysteresis can happen in electronics for many different reasons, and it's really important to be able to model them because they can lead up to some really strange nonlinear behavior. And also hysteresis can be observed due to thermal effects, which is another really interesting thing. Now, I'm not going to look at thermal effect, but I'm going to look at this Nixie tube, which is a neon tube. Now, these things also exhibit hysteresis, and the reason for that is that you have to reach a particular strike voltage in order to be able to create the plasma gas to be conducting electrons through it. So once you reach that excitation point, then you get a nice flow of electrons, and then you don't need to maintain that potential through the ionized gas in order to continue the flow of current. The potential can drop significantly. As a result, you have this hysteresis effect between the strike voltage and the maintenance voltage for these things to basically continue to glow. Now we can capture that effect and we can measure it using the source meter, and we're going to use this feature in Kickstart software that's called dual sweep. And all dual sweep is that essentially that it increases the voltage to the point where you specified, and it then decreases it back. So it does a double sweep, as the name suggests. And I have here set it to go from 100 volts to 200 volts at half a volt steps, and I have limited the current to 10 milliamp. Make sure you do that, otherwise it's going to continue putting more and more current through the Nixie tube and eventually destroy it. And here, as you can see, the delay, there's a delay parameter here also where you can set how long it will wait between the points, and you can use that if you want to capture thermal effects. Let's say you're measuring a transistor that gets really hot at some bias current, and on the way back down it won't traverse back through the same IV characteristics, so you can capture thermal effects and play with that. So for us, we're only going to look at the Nixie tube's natural hysteresis behavior. So let's go ahead and run this, and this is now disabled. This is from a previous run, so you can see the light is off, so it's not actually running yet. So I'm going to go ahead and start the test. Here we go. So it's running now. You can see the voltage steadily increasing, and it's still below the strike voltage of the neon tube, so it's not on yet, and then it's going to turn on. There it is, there it is. Now it just starts conducting, and electrons are flowing. The current is going to go rapidly increasing, and it's going to hit 10 milliamp. Once it hits 10 milliamp, then this is going to go into a voltage limited mode, a current limited mode, and you can see that the voltage stuck. Now the voltage is increasing still, program voltage is going up, and it's now at 200 almost. It's going back, so it's on its way back down. Now if you were to go ahead and look at the graph, look at this. Look at the graph and look what's happening. So this was the initial strike voltage. Now it's not coming back over the same curve, and look, it doesn't actually go back to zero at the same point. So this hysteresis effect now fully captures the behavior I was talking about. Now the sweep is now finished. So let's take a look here. This is the hysteresis effect. So we can go ahead and zoom in. Let's see. There it is. Oops, that's not what I wanted to do. There we go. We can look in here a little bit more carefully. There it is. So this is a voltage where it begins, when the conduction stops on the way back once the current has been already flowing, and this is the initial strike voltage of the neon tube. So you can see the full hysteresis effect in play, and even at the very top, all the differences can be examined. And the nice thing is that you can always take this data out of this software and put it into Excel or in MATLAB and something and fully analyze this. But even more interestingly would be to measure something that has a thermal effect. And for the interest of time, I'm not going to go ahead and do that right now, but you can see that capturing hysteresis is quite straightforward with this instrument. So I decided to do one other thing before we move on. Since this unit is able to measure such small resistances, it can also measure tiny changes in resistance. So I have made here a little makeshift resistor here. You can see it's just a couple of winding of wire that are separated, and I have 4 wire connections right to this point, so the instrument is able to measure the resistance of this coil. And I have connected it, you can see here, through the 4 probes going on to the terminals of the instrument here, and I can go ahead and enable the output, and you can see that the resistance is 0.141 ohms, and this is really sensitive. I can just blow at it. You can see that the resistance changes just from the warm air from my breath. So it can measure tiny changes in resistance. Remember, this is milli. This last digit here is micro ohms that we are looking at. So what I thought is, well, let's see how much we can reduce the resistance of this wire if we were to put it into an extremely cold environment. Well, I have a dewar here, a glass dewar, which you may have seen from my previous video, which is a double layer isolated with vacuum in the middle. So we can go ahead and put this resistor directly inside it, like so, and lower it all the way down. There you go. Now it's sitting at the very bottom, like so. So here it is. You can see it sitting at the bottom of the dewar. Now there's nothing in the dewar, of course, and so you can see the resistance at room temperature. But what I can do is I can go ahead and add liquid nitrogen to the system and bring the temperature down to almost minus 200 degrees Celsius. And from there, we can see how much this resistance will drop. So let's remember that value we're looking at, and let's add some liquid nitrogen. All right, you have your eye on the display. I'm going to go ahead and pour some into a funnel that I have at the top. Here we go, so 0.141. Here we go. Whoa. Look at that. That is pretty amazing. Now the temperature is going to equalize and the boiling will stop. You can wait a few moments until the boiling stops. You can see that the coil is fully submerged inside liquid nitrogen and is rapidly boiling, and it's going to do so until the inside temperature of the dewar will reach minus 200 degrees Celsius and the boiling will stop. As you can see, it's about to do that. So a lot of it evaporated in that process. You can see it's almost stopped now, and look at the resistance, 0.0017. So it dropped by about a factor of 10 or so, 10 times less resistance. And we can easily measure that. There's no challenge whatsoever. And in fact, if you know the resistance coefficient, the resistance coefficient of this particular metal that this is used, you can actually measure the temperature directly in there. You can program that into there and find out what the temperature is by using this mechanism. It's not the most reliable way. Of course, the thermocouple is better. But I thought, hey, we have liquid nitrogen, we can play with it and find out what we can do. And look, no problem, we still have many more digits. And don't mistake that this is not superconductivity. Liquid nitrogen is far too warm for superconductivity to even take place. You need liquid helium, you need temperatures as low as 4 degrees Kelvin. This is far too hot for that. All right, well, let's move on. Oh yeah, and here it is being taken out. Ah, look at that. Awesome. And you can see the temperature slowly rising back up, and it will eventually reach what it used to be before. If I were to touch it and heat it up much quicker with my finger, you got to be careful because you're going to get frostbites. You can see that it's going to rapidly go up. Pretty awesome. So for the next experiment, we're going to take a look at supercapacitors. Now, measuring the capacity of a supercap using traditional LCR methods, it's not possible. And the reason for that is because LCRs use essentially a dynamic measurement. They look at the frequency response of the capacitor itself, and that way they can estimate the resonance frequency and the quality factor of the capacitor at different operational frequencies. So they use the frequency response at time constant in some way to measure the capacitance. Of course, where something is really large in capacity, it's not practical to do that. You will have to measure the capacity of a supercapacitor the same way you do of a battery. For example, this one that I have here is a 2.5 volt 400 farad capacitor. It's a reasonably large supercapacitor, but don't be fooled. These things are not, they do not have more capacity than batteries. So this thing has a capacity of about 1250 joules, which is half of CV squared, and that's how you can calculate that. But even a tiny battery like this one, this is a 320 milliamp hour lithium polymer battery, and if you assume its voltage on average is about 3.5 volt, that works out to be more than 4,000 joules. It's already almost 3.5 to 4 times more capacity than this here, and it's significantly smaller, and it weighs much less. The strength of a supercapacitor is not in its capacity, but it is in the fact that it can be charged and discharged at many times the current than a LiPo can, and it can also survive at much higher temperatures and much lower temperatures and maintain its capacity and the charge that's stored in it. So it's not really beneficial because of its capacity, but because of its specific abilities, its properties that it has. So we're going to go ahead and try and charge and discharge it, and in order to do that, we're going to actually use a code that I've written, a script that I've written that discharges the capacitor and then tells you what the capacity was, and I'll talk about that. For now, let's go ahead and just charge this guy using a straightforward method, using this bottom source meter. Again, it's very easy to do that. Let's set the limit of the current to 1 amp. Like I said, you can charge these guys at a very high current, and 1 amp is the maximum the source meter can give us, so let's go ahead with that. I'm going to limit the voltage to 2.5 volts, like so. And I'm going to go ahead and connect this guy to the battery. Let me make sure I'm on camera here, like so. There we go, we are connected, and you can see there is some residual charge of about 125 millivolts on the capacitor. No problem, we're going to go ahead and turn it on. At this point, all I'm doing is charging it. You can't find the capacity by charging it directly, and there's a very good reason for that. I'll let you think about that separately. For now, we're going to let this charge up, and while this is charging, let me show you the code that I'm going to use. So Keithley provides this software called Test Script Builder, which allows you to write your own script and then save them or upload them to the instrument. Again, I'm sorry I'm recording the screen again. I noticed in the previous section that some of the stuff was not in focus, so I apologize for that. Hopefully this is better. And so here you can see I've written a whole bunch of statements that will do what I just described. It will characterize the capacitor, measure the total amount of energy stored in it, and display it. Now the really nice thing about writing these scripts is that first of all it was really easy to get started because the script description of all the syntax is explained inside the manual, and you can really get up to date. If you've run any programming, you can get up to date and running in no time. So what this code will do is that it will turn it will basically make the instrument to be completely standalone, and it will even bring up pop-up menus and little instructions for the user telling them when to connect things and when to disconnect things, which can be really handy if you're writing something in a production environment and that someone else will be executing the code and you're not there yourself. You can write all the instructions and all the messages. You can even ask for user to enter parameters. It's really handy. It's a full-fledged programming environment. You're essentially writing code to another computer, which is the Keithley 2450. So I'm really impressed with it. It's one of its strengths for sure. So this program will go through it. It will so for example, let me just give you a quick overview. I don't expect you to follow the code, but so here we go. So it sets the source, it sets the measurement mode, and then at the bottom here it has a for loop which continuously checks the voltage and the current of the capacitor, and once it reaches to a point where it's depleted, it could be of a battery also, when it's depleted then it will terminate the loop and then it will report what the total capacity was. So I'm not going to show you this anymore. We're just going to download this into the instrument and it will be standalone, and we'll go from there. Here we go, it's pretty much completely charged now. It's going to take a much longer time for that little bit of current to also go through, and we can go ahead and measure its capacity. It's going to be a little bit lower than what it actually is, but that's okay. It serves the purposes of our experiment. So I'm going to go ahead and run the code, and you can see what happens as soon as I execute it. Again, you can execute it directly in here. You don't have to use the computer, but I'm going to initiate the execution process, and you can see my code now prompts the user to connect the DUT, the device under test, which is in our case the capacitor, to the unit itself, and then press OK. So it's just now waiting for us to do this. It's useful to put these kind of things in your script to guide someone else who might be doing the measurement. So let's go ahead. We're gonna turn this guy off, disconnect these two cables, make sure they're not touching each other, and I'm going to connect the main discharge cable back here and this one as well. And I'm going to go ahead and connect the sense port back onto the top source measure unit, and the reason for that is because we're going to discharge this at a high current and we want to measure the correct voltage across the capacitor. I'm going to go ahead and press OK. There it is. So now it's going to run and discharge it. So I have written the code in order to prompt and to display how long the measurement's been going on, what the current voltage of the capacitor is, and what the discharge rate is. So you can see it's discharging at 1 amp, which is the maximum that the source measure unit can do. And then you can see the voltage being counting down slowly, and it tells you how long it's been going on, 20 seconds or so. And if I can still swipe left, it's going to show me the current, which is pretty much constant at 1 amp. It's not really changing. It's just a small fluctuation there. So I can go back to this thing and just wait, and when it's finished, it's going to pop up another message and tell me what the capacity was. And again, once that code is done, you can run it over and over again and just have the unit as a complete standalone computer essentially. It doesn't have to be connected to anything. So let's wait a little bit until it fully discharges. Here we go, we are almost there. We're at 0.1 volt. And just one thing to note here is that I'm not accounting for dielectric absorption here, so I'm not going to wait and discharge it again. Just keep that in mind. So it's somewhat of an approximation because of that fact, but it's not so bad. So let's see, I almost finished. It's going to reach 0 volts now. Come on, just a few, 50 millivolt now. And again, you can still continuously discharging at 1 amp, even at 40 millivolts, of course, because this is an active source, so it can do that. And once it's finished, it should report us the total amount of stored joules as well as the capacity. Let's see, almost there. And here we go. There we go, look at that. There it is. So it's telling us that the total amount of energy was 1,133 joules, about 362 farads. So, you know, this is rated for 400. I didn't completely charge it. I'm not accounting for the electric absorption. But anyhow, it's a pretty good measurement, and you can do it more accurately, of course, when you spend more time and do it. Do the things that I mentioned, but you can see that this unit can be easily programmed with a script to do any kind of discharge and charging and measuring. And you can also do things like lifespan on something like this. You can have a unit charge and discharge at various rates and stress a particular component for a long time and see what happens. So now that the script is in here, you can run it over and over again. So let's move on to something else. So here's the setup for our next experiment, which involves wireless power transfer. So one of the very typical problems for a wireless power transfer is that the efficiency as well as the maximum power transfer of a wireless system like this drops drastically with the distance between the two coils. So here I have a setup where I have a transmitter and a receiver on top of each other. I'm going to give you a close view of this. And I can go ahead and change the distance between the two coils by changing the knob on this little actuator here. So I can essentially lift the other coil at a particular distance from the bottom one. Right now the coils are sitting perfectly on top of each other. So let me go ahead and zoom into here so you can see. There it is. Now you can see a better view of it, that the bottom coil and the top coil are essentially on top of each other. That's as close as you're going to get them in any real application. And you know, everything is quite far away from all the metals. The field is reasonably contained within at least one diameter of these coils, so there's nothing around it that can interfere with it, and the table is made of wood and is quite, you know, separation is sufficient. So you can see that here's the transmitter little board, and here's the receiver little board. These things are quite small, and you know, you can pack them into cell phones, and you've seen wireless charging has become rather popular. So what we're going to do in this experiment is that we would like to characterize the efficiency as well as the maximum power we can get from one of these modules as a function of distance. So now you can imagine this is a rather repetitive measurement. So what I've done is that I've written a script for the top source meter up here, which will search through and find out what the maximum power we can get at a particular separation is. And the bottom one just provides power to the transmitter. So this is a fixed source, and it's supposed to run from 9 volts. I've already set it up. I've set the maximum current to 1 amp, and I've set the source to 9 volts, so I can go ahead and turn on the bottom source like so. So you can see that it's providing us with 9 volts and it's consuming about 80 milliamps, but the top coil is not consuming any power. So this power dissipation is just essentially wasted. It's the power required for doing the creating the AC current in the coil and creating a magnetic field, and the loss is in the coil itself, and there will be some eddy current and some absorption in the top coil, even though I'm not drawing any current from it. So now what I can do is I can go ahead on the computer and I can run my script. I'm going to start the script right now. There we go. Now there is a little warning thing that I've programmed into the unit, and the unit is now saying set the desired coil separation, which I've already done. The coil separation right now is at its absolute minimum, so I can go ahead and say, okay, well, I'm satisfied with that. Go ahead and measure this for me, so I'm going to go and click OK. I hope you can read that. Here we go. We're going to click OK. And now you can see it says searching, so it's going to search for me, and it's going to go ahead and continuously increase the current consumption until the voltage drops below a certain value, and I've set that value to be 4.75 volts. Below that, I assume that it's not working. There it is. It stopped. So at 4.7 volts at the terminal of the instrument, I can get as much as 650 milliamp at a voltage of 4.73 volt, which is equivalent to 3 watts. There it is. It just, for me, is just searched for and characterized the wireless power transfer and told me that, well, at this separation, the best you're going to do is 3 watts under these conditions for 4.7 volt. And now I can go ahead and easily calculate the efficiency of this system under these conditions. I could have programmed this system to even tell me the efficiency, because I can talk to both of these units, but you know, for simplicity, we can do it very quickly on the calculator. So the power consumption of the system at the bottom is just the current times the voltage, and we know we can get 3.07 watts. So we can go ahead and do a quick division. 3.07 divided by 9 volts times 0.633. There it is. So it's about 53-54% efficient, which is not bad. It's pretty good. But of course, this efficiency is under the condition that the coils are essentially touching each other. So now what we can do is we can go ahead and increase the distance between the coils. So let's go ahead and run the code again. and I'm about to run it here on the computer. There we go. So now again it turned the source off, the current consumption went back to normal. Now it's saying set the desired coil separation. Okay, no problem. Let's go ahead in here and let's increase the coil separation a little bit. I'm going to turn this actuator here, and you're going to see that the coils are going to separate from one another. There we go, we're getting a little bit of separation. There it is, you know, that's not too bad. Let me lift the camera so you can see what I'm talking about a little bit better. Here it is, you can see now. Sorry for the shaking. There you go. I hope this is going to focus. There, you can see that the coils are now separated by a couple of millimeters. You can, you know, have a little ruler next to it that measures their separation and so on. It's pretty straightforward. This is now a few millimeters or so. So let's go ahead and put the camera back. There it is. So we've set our separation. Now let's go ahead and once again initiate the search for the maximum power. There we go. It's now searching again. 5 milliamp, 10 milliamp, 15 milliamp. It's going to keep going, and you can see the voltage is dropping already. Voila, and it stopped. So it just became half as much as it could do before. So now the maximum power I can get at this separation is equal to 1.4 watts, significantly less than I had before. And we can go ahead and calculate this efficiency one more time. So now we have 1.4 watts divided by 9 times 0.275. There you go, about 56% or so. Not too bad. You can get quite a bit of, usually the efficiency of a system like this is between 40 to, you know, maybe 55, 60%. That's the most you can do. So, not too bad. We're getting almost more than half the power into our system. Let's do it one more time. There it is. We're going to run it again. There we go. So now it's asking us again to change the coil separation. Let's go, you know, rather large this time and separate them quite a bit far further from each other. I'm going to rotate and keep going for until we are really satisfied. You can see now, even at this angle in the camera, it should be fairly obvious that the coils are quite a way far apart from each other. There we go, perfect. Let's go ahead and initiate one more time. There you go. It's going to search 10 milliamp, 15 milliamp, and there it is. It couldn't do more than that. So you can see now, actually it already dropped the next, because I'm incrementing it by 50 milliamps at a time, it's already at 4.2 volts, so it's quite a bit more. So this number is a little bit optimistic, let's say about half a watt. So, you know, by separating it, you're going to lose a significant amount of power because this magnetic field, of course, degrades with distance quite rapidly. As a result, the amount of magnetic flux that can be captured by the top coil is going to reduce significantly as a function of distance. But you know, the point that I want to get across is that you write the one script, you load it on that. It doesn't really even need to be connected to the computer, as I've said so many times already. You can just load it up and run it, and then you can run it over and over again and get a full characterization. You can even do even fancier things and automate this and have this connected to a separate motor, you know, and have everything run in one giant script on multiple of these units and get some serious automation going on. Look, that looks great. So let's do one more experiment. So for our next experiment, we're going to look at some optoelectronics. So here I have a photodetector, which is in a pigtail module, and you can see the fiber coming in, and it gets coupled inside this module into a PN junction diode, and the arrival of photons is going to create a current when the photodetector is reverse biased. Now I know nothing about this photodetector. I don't know its responsivity, I don't know its dark current, and therefore I do not know how to relate the electrical current to the optical input power. But if I could put a known optical power into it, then I can find all the unknown parameters of it, and then I can use it to measure optical power coming in. Now what I'm going to do is I've written a script for the Keithley 2450 in order to do just that. So the Keithley 2450 is going to run that script. First, it's going to characterize the photodetector, measure all the parameters in order to know exactly what to expect, and then it's going to turn itself into an optical power meter, and it's going to give me optical power, no matter what that is, into the diode, within the diode's linearity, of course, and then it's going to change the display to show optical power as opposed to current and voltage. And this is the power of being able to run any script you want and run any mathematics behind the script and run very complex calculations in the background, although this is not very complicated, but it can do really fancy stuff. So we're going to turn this guy into an optical power meter. Now the setup is a little bit complicated, so it's going to take a bit of explaining. So bear with me as I take the camera out. I'm going to follow all these fiber optic signals in order to figure out exactly what's going on. So let's start from our laser source. So for the laser source, I'm going to use an Agilent A3433A, which is a lightweight transmitter. And this lightweight transmitter has a laser diode built into it, which puts out quite a bit of power, about 10 dBm or even more, at a wavelength of 1552.52 nanometer. But the output power is fixed, so I cannot adjust it. Therefore, I cannot give it a calibrated output as I want to. So what I'm going to do is I'm going to I've taken the fiber out, and the fiber therefore then goes into an Anritsu MN9610B, which is a programmable optical attenuator. And you can adjust the attenuation like so, which means that whatever power you put at the input, the output is going to come out at that power, minus the attenuation. There is some insertion loss, about a dB or two. But aside from that, you can adjust the attenuation coming out. So therefore now, this red fiber that I have here is now a fiber which carries an optical signal whose power we can therefore adjust using an optical attenuator. If I were to follow this little cable, it reaches to this little part. This is an optical coupler, and this is a 10-to-1 optical coupler. And for all practical purposes, because 10-to-1 is quite a large ratio, you can think about it such that this yellow fiber therefore puts out 10 dBm less power than this black fiber, no matter what it is. So if I, for example, put in 0 dBm in here, then what comes out of here is going to be minus 10 dBm, and what comes out of here is going to be roughly 0 dBm. And this is a 10-to-1 coupler. It's similar to an electronic coupler that you can have a 20-30 dB coupler. This is just an optical version of the same thing. And then the black fiber goes into this yellow fiber, which is just used to convert the connector from the FC to a different type. And then it comes through here, and then finally goes into the detector. Now this fiber is we're going to use to measure the optical power coming in, and that's, if we follow that one, that's going to go into my HP86120B, which is the wavelength meter, which works quite well at 1550 nanometer. Right now the laser is off, therefore you're not reading anything. So if I were to read minus 10 dBm in here, because this is after the coupler, this would tell me that I will be getting approximately 0 dBm into the photodetector itself. So therefore I can do a calibration. So let's go ahead and turn the laser on. I'm trying not to shake the camera too much. Here we go, laser on. The light is now turned on. Let's take a look at this guy. Set to 0 dBm. And then, oops, sorry about that. And then let's follow the fibers again. And look at that. So as expected, we're getting a wavelength of 1552 nanometer, .52, and at the power of minus 3.24 dBm. This means that the photodetector is now receiving the power of minus 7 dBm, power of 7 dBm, sorry about that. So you have to add 10 dBm to that. You will get about 7 dBm or so, which is a lot of power. So let's go back in here. Again, take a look at this. So there you go. So fibers come from there. And what we're going to do is now we're going to go ahead and run the script. Here you go, I ran the script. And the very first thing the script is asking, it says that disable optical input to measure dark current. Okay, so what I'm going to do is I'm going to go ahead and press the shutter button of the attenuator. Now if you go ahead and look at that, if I press the shutter button, I'm going to press it right now. There we go, and you can see the optical power disappear. So if it's measuring nothing, it means the optical power is well below 60 dBm or minus 50 dBm. Okay, that's perfect. So now I can go ahead and say that, okay, I've done that, so I'm going to press OK. Then it's going to do a measurement, then it's going to ask me, okay, now set the optical power to 0 dBm to measure responsivity. So now it's going to calibrate the photodetector for me. Okay, so let's go ahead and do that. I'm going to again go ahead and turn the shutter on. So we will see the optical power come back. Here we go. Minus 3 dBm, just like it was before. And I'm going to dial in some attenuation in order to get this number to show minus 10. When this shows minus 10, I have about 0 dBm into the photodetector. So let's go ahead. Here's 1 dB attenuation. Let's go 6 dB attenuation. There we go, one more. 7 dB attenuation. There we go. So at 7 dB attenuation, it's almost dead on. There it is, 10 dBm. Let me just show you that again for completeness so that you don't think any of this is magic. Here we go, 7 dBm attenuation results for us a 0 dBm of optical power. Perfect. So let's go ahead and put that back. And let's go and look at this guy. Okay, well, we've done that. So now I can go ahead and say, okay, And look at that. It did everything for me. Now it says your dark current was 680 nanometer, 680 nanoamps. And the responsivity is 1 amp, 1.05 amp per watt, which is actually really, really high. So this is a very, very high sensitivity diode. And it says that the measured power is right now roughly 0.41 dBm. Perfect. Let's see if it works. I'm going to go ahead and dial more attenuation. Okay, so remember what we're comparing with is that this number should be 10 dBm below that number, which it is right now. So let's go ahead. I'm going to dial in some more attenuation. So it's now 7 dBm. Let's go 8 dBm. Look at that. It became minus 0.5, which is 1 dBm below. Let me go now 9 dB attenuation. There you go. See, 1.53. Let me go 12 dB. You see, minus 4.46 dBm. So now we have an optical power meter. I just turned this thing into an optical power meter just by a very simple script that I've written. And look, no magic. See, minus 14.9. This guy should be 10 dB less than that. And it almost is. So it's working really, really well. Now we have an optical power meter at our disposal. Now that we can measure optical power meter easily, we can now use the second source meter to characterize a laser diode. There you go. So I've disabled the optical power at this one. So now it says NaN, which means not a number. So because the power is too low for it to do any real measurement. But now what I've done is that I have connected the bottom source meter to a laser diode module, and this is also a pigtail module, and you've seen this in one of my previous videos. So I'm going to put current through this laser diode, and this laser diode is going to therefore generate optical power at around 1550 nanometer as well, and then the output of that optical power is taken and then coupled directly into the laser diode. Because we have calibrated the laser diode and we know we can count on its power measurement report through the source meter, now we can go ahead and measure optical power as a function of current from this laser diode. So I've programmed this guy to put 1 milliamp through the laser diode. Let's go ahead and turn it on. There we go, look at that. Minus 31 dBm, and the M just got cut out because this is too many letters. I should probably cut some of that out. So it should be dBm, not dB. It's just not displaying it. So minus 30, so if I were to put 1 milliamp through the laser diode, it's going to produce a voltage of 0.75 volt across the diode, and it's going to generate minus 35 dBm of optical power. So I expect to be able to generate much more optical power if I increase the current. So let's go 5 milliamp instead. Look at that, now it's minus 26 dBm. Let's try 10 milliamp, minus 19, and I can keep going. I can put more current through it. This should be able to generate a lot. There you go, minus 4 dBm. So it is really, really straightforward. In order to now you can imagine I can write a script now to do a two-dimensional sweep across all of these parameters and get a complete characterization of the laser diode, of the photodetector, and all of that can be automated. Right now I'm just punching this myself to show you, but you can imagine how easily this can be extended to do far more complex things, and it is invaluable in an optoelectronics industry. So we could even do more things. For example, we could go ahead and characterize this guy, which is a Mach-Zhender modulator. But for the interest of time for this video, I'm not going to go ahead and dive into that. But you can get the optical response of the Mach-Zhender modulator the same way we characterize the optical response of the laser diode and the photodetector. And now that we have a calibrated measured photodetector and we have characterized our laser diode over here, we should be able to really easily characterize something like a Mach-Zhender modulator. And then with two source meters, you have complete freedom to characterize the main three elements for an optical communication system so easily. And if you're in the optical industry and you're producing semiconductors, you really can't do without source meters. And that's why they're such valuable instruments. And what the key to the scripting capability and the LCD touchscreen and the sensitivity and the versatility of these units, you have to have these in your lab. Here we go, and I hope you enjoyed the review. There's a lot more that I can do with this. This has an entire trigger building functionality built into it, which if you go under trigger configuration, you can create your own triggers in any way that you want, and you can put all kind of conditions, and you can insert a particular type of trigger, whether it's an action or a notification or a branch, and you can put if statements, and you can wait for trigger lines that are coming from the outside. It's just incredible, and it's really easy to build this. I was surprised how this interface works really, really well. I was a little bit skeptical at the beginning, but man, it's easy to work with this thing. So there it is. I hope you really enjoyed it. And as I ask only for one thing. Please go ahead and rate the video. It only takes you a couple of seconds, but it makes a huge difference for me. And if you go ahead and purchase one of these, please let Keithley and Tektronix know that you purchased it. For example, if you saw my review and you liked it, I don't get any royalties from them. I get nothing from how many sales they have of these units, but it will help me have a good relationship with them, allowing me to bring you future videos of really interesting and unique instruments that come to the market, which you may not normally be able to see. And that's kind of what my website specializes on. So go ahead and do that. Leave a comment and give it a thumbs up if you like it. I would really appreciate it. Well, until next time.